Hello there, this is exercise 6b for, well, it's the pure core content for further maths, and this is proof by mathematical induction, which I've already looked at in exercise 6a, but that was with matrices. So I'm now going to extend those ideas to look at questions that say prove that something is divisible by something else. We all know what divisible means. Now, interestingly, it can be written in two different ways. It could be written as show that, as I just said, that, this is divisible by 4, for instance, or it could say show that it's a multiple of 4, and effectively it means the same thing, as I'm sure you realize from your GCSE maths. So a reminder of the 4 steps that we need to use, and we always need to use these. There's this 4-step process to prove things by mathematical induction, and the step 1 that I've seen and shown you before is that we just check that it works, and usually the base number that we check it for is n equals 1. These rules only ever work for what you call integers or natural numbers, so you don't need to worry about working for 1.5 or something like this. You only ever check for 1, for 2, for 3, for 4, going upwards. Then you do this rather bizarre step of just stating what seems to be the obvious fact. You assume it's true for n equals k. They've given you the rule perhaps for n, and you just rewrite it as k's. You prove it for the n equals k plus 1 case, so that's the tricky bit. And then we write out the completion statement. And as we saw last time, the completion statement looks like this. It's not the only version of it, but it's what I get my students to write out. So there is the completion statement. I'll be expecting you to know that off by heart. So here's an example. Now I've got 4 examples for you here. These first 2 are what I would describe as being with some help. You do get these, but you also get some without help. So let's just have a go at this. Now, first of all, it says we've got some sequence. It's defined by this this formula. UN equals 5n plus 12n minus 1. So it's just like a sequence formula. It's not iterative. It doesn't use the last term. I'm just looking at that. It just uses the value of n. So for instance, if I wanted to find a term, say like U3, I would simply do 5 cubed plus 12 times 3 minus 1. What's that? That's 125 plus 36. And then take away 1. That sounds to me like 160. I don't know if that's right, but it sounds to me as it should be. Now look, it says do a bit of algebra first. So, I mean, this is just me just getting a feel for the problem. It says do a bit of algebra first. Show that UK plus 1 minus 5 UK. So if we just think about that, that basically means putting k plus 1 into here, wherever the n is, and then putting k in, and then just doing a bit of algebra. So let's do that. So I'm just going to write this out. UK plus 1 minus 5 UK. U's are often used for sequences. I'm sure you've seen those before. So that's 5 to the k plus 1 plus 12 lots of k plus 1 minus 1. So that's the first bit done. I've done this bit, if you like, but now I've got to subtract 5 lots of UK, when that formula's kind of there, or formula, I've just got to replace it with a k. So it's 5 to the k plus 12k minus 1. I've got to be a little bit careful with minus and minus in brackets going on there. Anyway, let's work this out. 5. Now, the one thing I noticed actually is that if I multiply it out, will give me the thing I've just written here as well. So I'm going to write this out. 5 to the k plus 1 plus 12k plus 12 minus that 1. I'll work all those out. But this is the bit I was on about. 5 times 5 to the k. You should be aware that's 5 to the k plus 1, because obviously that's 5 to the power 1. 5 12s are 60, so minus 60k. And 5 1s are 5, but minus and minus is plus, and that's why I said be careful of that. So what have I got? Well, the 5 to the k plus 1s go. I've got 12k minus 60k. Well, that's the minus 48k. I assume this is the 16. 12 to k 1 is 11. Yes. 16 minus 48k. So hopefully you've got the same thing there. And now I want to do this second part, B, hence proved by induction. And this is obviously the main body of what we're doing here. So I'll just do B over here. I think I've got some space on the next slide as well. And it says prove by induction that each term is divisible by 16. And this is where the help comes in, because I already know this is true. I've just proven it's true. So let's go through the four-step process. I said step one, you check that this rule is true for n equals 1. So I'll do that. So I just got to put 1 into this. I've got to do u1. I've already done u3. u1 equals 5 to the 1 plus 12 times 1 minus 1. What's that? That's 17. That's 16. Yes, that is true. Now notice we are trying to show it's divisible by 16. And it's true. It is. That's meant to be a tick. It is true for n equals 1. So we've done step 1. Step 2, if you recall, said assume this rule is true for n equals k. Now this is, I always think it's a bit bizarre. Why am I writing this out again? But there you go. We're just going to write it down. U to the k. Now I'm going to write out this formula. It's obviously 5 to the k plus 12 to the 12k minus 1. But that's actually not the bit I care about. The bit I care about is it's a multiple of 16. So if you like, I could have written UK is a multiple of 16. Now, I think it's much more useful to write this here instead of writing this UK equals this, which it is. I want to write it as equals 16 times something. And since it's a multiple, I'd normally use n or k to be honest, but since it's a multiple, I'm going to say 16m. So I'm saying UK is equal to 16m, where m is an integer. Now, there's lots of quicker ways of writing that, but where n is an integer. And that's basically what we do. Now, that's the first two steps. So there's needs now to do the next two steps. So step 3, let's write this over here, was prove this is true. So you prove it for n equals k plus 1. And for n equals k plus 1, well, this is where we use our bit of magic here that we've already been taught. I can write out that formula. I write UK plus 1. And what was it? It said minus 5 UK. Hope you don't mind me jumping backwards and forwards. Equals, oops, wrong one. 16 minus 48k. So that's what I now know is true. And this is where my assumption that I know what UK is comes in so handy. Because I know that UK plus 1. This UK I wrote as 16m. So really this is like 5 lots of 16m. That's what the UK was. Do you remember that in step 2? And of course that's equal to the 16 minus 48k. Now, it doesn't take much to move this onto the other side. I want UK plus 1 on its own. So that equals 16 minus the 48k. I reckon plus, well, 5 16s are 80m. And if 80m, I mean, the great thing about this is now I can rewrite this as a multiple of 16. 16 comes out as a common factor. I get 1 minus 3k. Oh, look at that. I'm going back to 5m again. And the critical thing is, if k is an integer, and it is, and m is an integer, and it is, this equals, basically, this must be, I'm just going to write, which is a multiple of 16. Now, the completion statement, by the way, that's step 3 now done. I've proven it's a multiple of 16. The completion statement is this wordy bit, and in the exam, step 4 would be writing that out. Now, that's one example then. Let's do another example. This one is also with some help. It says the sequence is defined by this. So find U1, U2, U3. So all we do, we're chucking these in. U1 is 5 to the 1 plus 2. Well, 1 minus 1 is 0. So that's like 5 plus 1, which is 6. U2 is 5 to the 2 plus 2 to the 1. You'll notice the power is always 1 less than the second one. What's that? That's 25 plus 2, which is 27. Okay, so far, what's a U3 as well? So that's 5 cubed plus 2 squared. 5 cubed is 125, so this must be 129. So hence suggest a positive integer other than 1 which divides exactly into each term of the sequence. Well, immediately I see 6 and 27, I'm thinking 3's. And looking at 129, I think 3's go into it. So I think 3 is the magic number there. By considering un plus... Oh, look, this is the help bit. They're telling me to look at this. So, okay, I'll do exactly what they say. First of all, let's do my 4-step process. Step 1, check for n equals 1. And as it happens, I've already done that. I've done it up here. 6 is a multiple of 3. So that seems to be right. So this is what I'm going to try to do. I'm going to try to prove it's a multiple of 3 because this was my magic number here. 2 was assume. So I can now write here, assume that, well, my formula was un. Un is a multiple of 3. If you prefer, and I certainly do prefer, I like writing it like this formula approach, un equals 3m, where m, well, the posh way of writing this is belongs to the natural numbers, or you might write this as it belongs to the positive integers. Best to say it's positive. We don't really want, no, and it even says positive up here. So let's go with this a bit further. I need to do step 3. And step 3 is where I'm going to use their bit of help here, this un plus 1 plus un. So let's do what they've said. Step 3, I'm going to try to prove for n equals k plus 1. And the way I'm going to do it is, it says there, it says write out un plus 1 plus un. So I've got un plus 1 plus, well, I suppose I should be saying uk. Let's do this properly, switch the letters, because I'm proving this for the letter k. What was this equal to? I can't even remember. It was 5 to the n plus 2 to the n minus 1. That's right. So uk plus 1. So it was 5 to the n plus 2 to the n minus 1. That's what un was equal to. So if I have uk plus 1, I reckon that's 5 to the k plus 1 plus 2 to the k plus... Now, what's the other bit? I've got uk. Well, that's just those bits. So that's 5 to the k plus 2 to the k minus 1. All right, and so I've written out what they've told me to do. Now, the first thing I notice, actually, is this 5 to the k plus 1. Now, you've got to be able to think of this as, well, it's 5 times by 5 to the k. And that's the subtle trick. Really, that's 5 to the 1, I suppose. And you should recall you add the powers. So I've changed this part so that it resembles this part, I suppose. Don't forget the plus 2. I've just realized I might want to do a similar trick. Look, this says 2 to the k minus 1. Now, this is the same as 2 times 2 to the k minus 1. This is the trick I'm going to use on both of them. That if I split these first two terms, I get very similar to the n2 terms. So I'll just finish off the n2 terms. And that little trick I've done, the first one I think is more obvious. 5 to the 1 times 5 to the k is 5 to the k plus 1. This one is less obvious. 2 to the 1 times 2 to the k minus 1 is 2 to the k. And the reason for doing this, because then you look at this and you think, I've got lots of 5 to the k, plus another 5 to the k, I've got 6 times 5 to the k. And I've got 2 times 2 to the k minus 1, plus another one. I've got 3 times 2 to the k minus 1. So this is looking good. Now, don't forget, this left-hand side, we've already assumed that this uk can be written as 3m, because it's a multiple of 3. That's our assumption in step 2. So we can write, I suppose here, we can write uk plus 1 plus 3m is equal to all this lot. And when I move that onto the other side, I get uk plus 1 is equal to, well, 6 times 5 to the k plus 3 times 2 to the k minus 1 minus the 3m. And of course that's great because I can take 3 out as a common factor. I get 2 times 5 to the k I get, well, just the 2 to the k minus 1 and minus an m. And the great thing is, because but you look at this, I mean, this is powers of 5, so this is going to be an integer, this is going to be an integer, this is an integer. 3 times an integer will mean it's a multiple of 3. So I can just write which is a multiple of 3. And we've basically done what we wanted to do. We've wanted to prove it was a multiple of 3. Now, don't forget, there is this step 4. Step 4 is where we write out this is the given result of k plus 1 replacing k. Therefore, if it's true for n equals k, it is also true for n equals k plus 1. Since it's true for n equals 1, it's true for all positive integers. Now, it's a bit of a faff, that, but you've got to learn it. You've got to write it down to get the final mark on these questions. Now, I'll just show you the next slide and the next question. I've already written out here that we're going to try to prove, using proof by induction again, that 7 to the n minus 1 is divisible by 6 this time. It is 6 this time. But what you'll notice, there's no help. There's no clue. So you just got to go about this the same way as before. Now, the critical thing then is no help. No, we've got to start using our brain a bit, but we're going to use similar ideas to what we have already done. So let's go through these 4 steps. First of all, let's just check to see if it's right. So we're going to check for n equals 1. So check for n equals 1. And you quickly realize that f of 1, notice the new notation, you could easily have written u1 instead, equals 7 to the 1 minus 1. And 7 to the 1 is 7, minus 1 is 6. And it wanted me to prove it as an integer of 6, so this is true. So good, so true. Step 2, we're going to assume again. Always assume for n equals k. And really, this is just doing no more than rewriting it. But if that's what they want us to do, then that's what we'll do. So f of k equals 7 to the k minus 1. Okay, that's fair enough. Step 3, what does step 3 want me to do? This is the tricky bit. This is the prove. Prove for n equals k plus 1. And I suppose I've got no choice but to go, I haven't got any clues this time. You know, a couple of times now we've been guided by the question, but here we've got to write f of k plus 1. And that is equal to, well, we've got 7 to the n minus 1. So 7 to the n, sorry, minus 1. And therefore it becomes 7 to the k plus 1 minus 1. And we've already seen this little trick that we've seen before, where we think of that k plus 1 and we go, hang on a bit, we can write that as 7 times by 7 to the k. Because that's like 7 to the power 1 again. And when we add our powers, it sorts it out. Don't forget the minus 1. We've got this minus 1 here. And then I look up here and I think, hang on a bit, I've got f of n. And this is what I need to get back to. You see, I have assumed that this is true. In fact, I've written this wrong. I should have written this is a multiple of 6. And of course, I've done this lots of times and then I forgot. So f of k equals, well, it's multiple of 6. So let's write it as 6m again. And you should technically write where m belongs to the natural numbers. Okay, so at least I'm now in the right place. There. And because I've got this f of k equals 6 of m, it would be really good to get back to that kind of scenario where I can write this as, f of k. So here's the trick, I suppose, is let's rewrite this 7 to the n minus 1 down here instead. Well, 7 to the k minus 1. But so I want, because it says 7 times 7 to the k, I want to write 7 times by bracket 7 to the k minus 1, because that would mirror what I've got up here. But of course, in doing that, if I multiply this out, it doesn't give me this first term. So you quickly say to yourself, well, a bit, I've taken away 7 too much, add that 7 back on. But like you do in completing the square, I suppose, don't forget the minus 1 here. And now I can write, well, this is, 7 to the k minus 1, 7 to the k minus 1, 7, that is 6m. You see, that is now 7 times 6m, because I know this thing is a multiple of 6. It's great. Don't forget 7 take away 1 is plus 6. And now I can take out 6 as a common factor. And 6 as a common factor is, of course, now I can write 7m plus 1 which is a multiple of 6. And I think we've done it. Well, not quite. We need, I suppose, to write out step 4. But other than that, I think we have done it. And this is that one done. So let's try this last final example, and it's again no help. Use mathematical induction to prove that for all positive integers n, 9 to the n minus 2 to the n is divisible by 7. It's the same, isn't it? So let's start off where, why not I just start off by writing, since we had that notation just now, I'm going to start off by writing fn is 9 to the n minus 2 to the n. I could easily write un again there. Okay, so now I've done that, I'm going to do step 1. I'm going to check, is this true for n equals 1? And that would be f of 1, which would be 9 to the 1 minus 2 to the 1, which would be 9 minus 2. You can clearly see that is 7. It is true. It is divisible. 7 is divisible by 7. Step 2, we do the assumption bit. We assume for n equals k. And again, I'm just going to write out f of k equals, what was it? It was 9 to the k minus 2 to the k. But I also want to write out, like I did last time, that f of k is 7m. Because it's a multiple. It's a multiple of 7, where m belongs to these natural numbers. So we've done step 1, step 2. We do step 3, which is where we prove. We're going to prove for n equals k plus 1. And here, I suppose what I need to do is write down f of k plus 1. There you go. Now look, what does, well, obviously if I put k plus 1s in here, I'm going to write 9 to the k plus 1. I see a similar trick to last time going on. Minus 2 to the k plus 1. Both of them have the same powers this time. And by the last time, the trick I mean, it's 9 times 9 to the k. Minus 2 times 2 to the k. So far, so good. What do I want to do here? I want to use a similar trick to last time. Now, last time, rather than writing 9 times 9 to the k, I kind of rewrote it like this. So I'm going to do a similar trick. I'm going to rewrite my f to the k, 9 to the k minus 2 to the k, rather than this 9 to the k. So it might seem a bit bonkers, but I think this will work. So I'm going to write a 9 to the k minus 2 to the k, because this thing I know is the same as f to the k, which I know is a multiple of 7, you see. So that's why I write it like that. But of course, I have taken away this lots of 2 to the k's by mistake. And therefore, I suppose I better add them back on again. So I've taken off 9 lots of 2 to the k, so I'll add those back on. 9 times 2 to the k, you can see I've literally just put them back. Oh, don't forget this bit as well. It says minus 2 times 2 to the k. So this is why we're doing it, you see, because I reckon that's 9 minus 2 is 7, which is a magic number. And I know this thing is this thing, and it's multiple of 7. So this can now be written as 9 times 7m plus 7 times 2 to the k. 7 comes out as a common factor, common multiple, and that therefore goes 9m here plus 2 to the k, which is a multiple of 7. That's me being lazy at multiple of 7. And of course I still need to write out the magic fourth step, which is this one, which is the given result with k plus 1 replacing k. Therefore, it is true for n equals k. It's also true for n equals k plus 1. Since it's true for n equals 1, it's true for all positive integers. But broadly speaking, I've now done it. So in summary then, we've now seen 2 types. We've seen matrices, where we use this little trick where m to the k plus 1 equals m to the k times n. And then we've seen this test for multiples and divisibility, sometimes with help, and we just rearrange their little formula. But with no help, you've got to do a bit of work, and that's the hardest bit. But it's not impossible, as you've seen. So we in class will do a few additional examples, but then essentially we'll do exercise 6b. Cheers, thank you very much.